Our next speaker is Haohan, and he's going to talk about intergraph node metric based on edit distance. Again, this paper came from VLDB 2017.
So hi everyone, I'm Haohan from Facebook. This paper, we published this paper in VLDB 2017, but we didn't make the trip, so thanks to the organizer moved the presentation to the Sigma this year. The presentation, this paper is about the intergraph node metric based on edit distance. First, I would like to introduce like the applications we are targeting from this like the project. We're trying to solve like the transfer learning problem on the graphs. So for example, one is about the communication networks. So we may have the communication network, it's a dynamic network, it changes day by day. But we can have the expert knowledge to label the node, to give the roles for the node, to mark the node. But if we have like the new communication networks, how can we use the previous like knowledge to tag the node roles or tag the node labels automatically? Another application is about protein-to-protein interaction networks. So biologists find so the similar structures in the proteins may have the similar functionalities, although they are targeting different like the things. So the one important part to find the similar proteins is try to find the similar node inside the proteins. And we found another like the application is about graph de-anonymization. Because when we deliver the graph data, we have to do the anonymization to hide the privacy information. But node similarity is a common use of the technology to do the graph de-anonymization. How to evaluate the graph de-anonymization and anonymization level, we need to evaluate the node similarity and to find best node similarity to detect this. And to do the abstraction, we find like all those applications share the similar properties. One is label-free. Because for some like the graphs, they may not have the same labeling systems. And even for some graphs, they do not have the label at all. So we cannot always leverage the labels. And the second one is intergraph. Because the transfer learning and the graph de-anonymization, we need to compare two nodes in two different graphs. That means like two nodes may not have the connectivities. And the next one is about the metric. Because to apply to those applications, we need to find the top k similar nodes or try to find kind of the most similar nodes. And then if the metric, the similarity is a metric, we can leverage all the existing indexing method which can hold for the metric space. We have the investigation about existing node similarity. And actually, the major part of the node similarity, they work on the two nodes in the same graph. For example, same rank and all the variants of the same rank. And then for the intergraph, the node similarity, they need to leverage some like extra information, edge label, node label, identifier, some of those information. And an important thing is many of them doesn't satisfy the triangular inequality. So that means that they are not metrics. They're good to measure the node, but they're not good to do the search. And then we come up with our proposal. It's a node similarity we call the NED. So we use neighborhood topological structure to describe a node. So that means we have the node, we construct the node signature, we use the neighborhood topological structure to describe this node. And we pick the k adjacency tree. So for each node, we can construct the k adjacency tree by just expanding to the neighbors. We pick the neighborhood trees rather than subgraphs because we can prove that if we want a node similarity which satisfies all the metric properties, one important thing is about identity. So the computation is as hard as graph isomorphism, which is known to be the polynomial time computable. But if we discard this important property, it will have the problem with like the top k similar nodes. That means like you may have like the multiple similar nodes with very small distance, but actually they're not exactly the same. Then after we have like the k adjacency tree to describe the nodes, the straightforward way is to use a tree ID distance. This is a common way. This is better than to make up some the features to describe this node. For example, the number of nodes, the number of leaves, the depths, because they do not satisfy the identity. But the problem of the tree ID distance is it is incomplete, and it's even hard to approximate. And then we introduced one restriction to have this modified tree ID distance. We introduced one restriction. We say the node operation can change the depth of any existing node in the tree. The tree ID distance can do that because if you remove or add a node which have the subtrees, it will change the depth of all the nodes in the subtrees. But we found this restriction makes sense because the depth of this node is an important property. It describes the distance between this node to the root, to the node we want to evaluate. So after we introduce these constraints, so actually we have three ID operations in this modified tree ID distance. We can insert a leaf node, we can delete a leaf node, and we can move a node at the same level from one parent to another parent node. And advantage of this modified tree ID distance is one is still the metric. It's the same as the tree ID distance. It satisfies all the metric properties. And the second is it's efficient. We have the algorithm can do it in polynomial time. And so next I will use an example to illustrate how we run this algorithm. So briefly, so the algorithm is bottom up from leaf to the root, and okay, I don't know. There should be some identifier in this part. And so for each level, we do the same procedure. We have the 6 part for the algorithm. First is padding. We need to pad 2 nodes to have the same number of the nodes. And padding cost is one part of the cost to contribute the ID distance. Later, I will introduce another cost. And after the padding, we will do the canonization. It's similar to the tree isomorphism algorithm. We do the canonization. For the leaf node, we can just assign 0 to them because they don't have any kind of child. They are equivalent. And then we construct a bipartite graph for this one. So the node will just connect to each other. And then we calculate the bipartite graph matching the cost. The matching cost is the other part of the ID distance. So for this example, right now for this level is 0. And then after the bipartite graph matching, we do the recanonization. So we realign the node in the same level. And then we move forward to the next level. So we still do the padding and do the canonization based on the subtrees. And then we construct the bipartite graph. So the bipartite graph is a complete bipartite graph, and the weight between 2 nodes, the node in the left side and the right side, actually the weight between the node in the left tree and the right tree, and the weight exactly the ID distance to change from the one node to the other. So then we calculate the bipartite graph matching, and we found for this level, the matching cost would be 1. But remember, because in the last level, we do the padding, so we do not want to duplicate the cost. So the matching cost, we do the adjustment, and it's still 0. And we go do the recanonization and go forth, and to the padding and canonization, bipartite graph construction and matching, and then calculate the matching cost. And then finally, we go to the root. So this is how we calculate the tree ID distance. We use the 2 types of the cost. One is the padding cost, one is the matching cost to calculate the tree ID distance. And we have the correctness proof in the paper to prove this algorithm can calculate the correct modified tree ID distance. So yeah, so this is the work chart for each level. So for each level, we do the padding, canonization, bipartite graph construction, and matching. and calculation for the next level. And in terms of the time complexity, we can do the padding and canonization in linear time. But bipartite graph construction, we need to do the n square. And bipartite graph matching, right now in the implementation, we use the naive solution that's n cube. So that means the bottleneck is about bipartite graph matching, and this algorithm is running n cube for each level. And we compare with the original tree editors and graph editors. We know they're not polynomial time computable, and we use the common use A star algorithm to calculate the tree editors and graph editors exactly. And we found when tree size increased more than 10, it's not even computable for tree editors and graph editors with A star algorithm. And we found the modified tree editors is a good approximation of the tree editors, even though we introduced one constraint. Because we find in the real world case, to change the node level is not a common case. So that's why we can achieve the similar distance between the modified tree distance and original tree distance. And then we found the modified tree distance is a metric for trees. And it satisfies all the metric properties. We include all the proofs in the paper, and then we infer that the node metric here is still satisfy all the metric properties, and it can evaluate intergraph nodes. So this is about efficiency. We found for the tree size increase to 500 nodes, we can calculate in 1 millisecond. And we found along with the tree level increase, the time increase exponentially. But for the small word graphs, the k won't be very large, because the k means how many hops you will jump, and to use that adjacency to describe the node. When k is very large, so that means you use the whole graph to describe this node. And then we use the de-anonymization as a use case to evaluate this node similarity. And we just examined the common anonymization algorithm. So one is naive algorithm, just a hide identifier, and one is a specification, and one is a permutation. And we find we compare with another node similarity, which is a feature based. So that means we have the one node, we extract all the features from neighbors, the degrees and the edges inside the ego net and all other features. And we found by using the tree distance, which keeps all the topological structures, can achieve the higher the de-anonymization success rate. We call it the precision. And yeah, that's proof that by using the topological structure, which is better than the features. And this is another the kind of the proof to say the identity is useful here, because the feature-based similarity doesn't satisfy the identity, and it will generate a lot of the false positives. And so that's all the presentation. Thanks.
We have some time. Finished early, so a few questions from the audience.
Yeah, sure. Yeah, so maybe I misunderstood. So you said both this graph at distance and tree at distance is NP hard, right? This is what they're NP hard.
Oh, it's not NP hard, it's NP complete.
Okay.
Yeah.
NP complete is NP hard. But anyway,
okay.
So, but I think graph at distance is indeed NP hard, that's fine. But tree at distance can be computed by dynamic programming in polynomial time. This is well known, I think.
That's isomorphism, right? If you calculate the distance.
You said you are talking about tree at distance, right? Not talking about isomorphism. Right?
Yeah, I mean, tree isomorphism can be calculated in polynomial time.
No,
but
at distance can be computed by dynamic programming. It's tree.
You mean how many ideal operations you use for that tree at distance?
Polynomial of the size of two trees. If one is m, one is n, you can do it. So there are a lot of algorithms. I forgot exactly the time, but maybe m times n, m squared. I don't know. So that can be done, I think, just by dynamic programming.
Yeah, could you send me
even
the reference?
Tree with bounded tree width, like some graph with bounded tree width, you can also do dynamic programming. So it's like a special type of graph. Okay. So I was maybe I misunderstood what.
I think I include the reference about like the proof about
we can
the
talk
NP.
offline.
Yeah,
if you
yeah.
want to know.
So or you can just send me the reference. You'll find like to solve that
you
in
can just
Parliament time.
wiki.
I think you need to discuss.
Yeah,
Okay,
offline.
everyone-
Okay.
Anybody else? So you mentioned that in practice, the move between multiple levels or different level doesn't happen. On what basis does it happen so frequently? So on what basis did you say that?
What do you mean the basis of?
The move operation. So now you're having a move operation within the same level, right?
Yes.
But in practice, you're saying that you don't see that in data where the move is from one level to a lower level or to a higher level.
Yes.
So did you analyze some data for that?
Oh, I just have the comparison about like how many times like the modified trade distance is exactly the same as like the trade distance. This ratio like indicates like how many cases like they want like moving the node between like the different level that happens. Because if this doesn't happen, so that means like they should have the output like the same distance. Only it happens, they may have the difference like the distance. So so that depends on the level. So yeah, so for the k equal to 2 and 3, so it could be up to like the 60% or 80% like the cases it won't happen. But for the 3 and 4 and 5, it will like be more cases, roughly half of them. Yeah, that is, but yeah.